All right, let's jump right in. When we look at a map, we see rivers as these simple, clean blue lines. But the reality is so much more complex. Their true shape, their actual width and depth, their geometry is crucial. And getting that shape right is the key to understanding, well, everything from predicting devastating floods to managing entire ecosystems. Today, we're going to break down how scientists are using AI to build the most accurate map of America's rivers ever created. And you need to understand the stakes here are incredibly high. Right now, in the United States, an estimated 41 million people live inside what's known as the 100-year floodplain. That is a massive number of people whose homes and safety really depend on us getting it right when we try to predict where a river is going to go. So that begs the question, right? With so much on the line, with all of our incredible technology, why is it that floods can still catch us completely by surprise? Well, it turns out a huge part of the problem goes back to something really fundamental we've been struggling with for decades, knowing the actual size and shape of the rivers themselves. To really get a handle on that risk, you have to start with the container. It's that simple. Before you can predict how much water is going to spill out, you first have to know how much water the river can even hold. Think about it like a bathtub. A river's capacity is all about its geometry, how wide it is and how deep it is. If your measurements for that tub are wrong from the start, then every single prediction you make about it overflowing is going to be off too. And for a very long time, our main tool for measuring the tub has been, well, let's just say it's been a little outdated. Believe it or not, for the better part of a century, scientists have been relying on a method that's about 70 years old. It's a pretty straightforward formula, but as we're about to see, that simplicity is also its greatest weakness. It's called power law hydraulic geometry, and that's a mouthful. But what it really is a kind of rule of thumb. The basic idea is that if you know the size of a river's watershed, that's all the land that drains water into it, you can make a pretty good guess about its width and depth. And look, for a long time, it was the best tool we had for making big landscape-scale models. But how well did it actually perform in the real world? Yeah, not so great, as it turns out. The report card wasn't pretty. To see why, we can look at this metric called R squared. Just think of it as a score from 0 to 1 on how well your model explains reality. For river width, the old formula gets a 0.45. That means it's only accounting for about 45% of what's really going on. And for depth, it's even worse, a dismal 0.18. Our foundational method was basically missing most of the picture. And this wasn't some big secret. The scientific community knew this was a problem. This quote basically sums up what everyone was thinking. To get better at predicting what rivers will do, we had to get much, much better at seeing what they actually look like. That 70-year-old formula had hit its ceiling. It was time for a whole new way of thinking. And this is where the story takes a fascinating turn. Instead of trying to find another simple rule, scientists decided to build something totally different, a digital hydrologist. Basically, an AI that could teach itself the incredibly complex patterns of rivers by looking at a ton of real-world data. Now, to pull this off, they needed 3 key ingredients. First, they needed a massive textbook for the AI to study, the HydroSWAT dataset, packed with over 220,000 actual river measurements. Second, they needed context, 17 different environmental clues, everything from the local climate to the soil type. And finally, they needed the students, 3 different powerful AI models, like a random forest and a neural network, each ready to learn in its own unique way. So how'd they do it? It was a pretty straightforward training plan. First, they just dumped all that real-world river data into the models. Then, they layered in all the environmental clues for each spot, so the AI had the full picture. And finally, they just let the models go to work, hunting for those incredibly complex relationships between the landscape and a river's shape, the kind of subtle patterns that a simple formula could never, ever hope to find. Okay, so the AI is trained up and ready to go. Now it's time for the main event, a direct head-to-head showdown, the classic 70-year-old formula versus these new data-hungry AI models. And honestly, the results weren't even close. Just look at this. It's an absolute game changer. For predicting river width, the AI model's score jumped from that old 0.45 all the way up to 0.75. And for depth, the improvement is just staggering, from that terrible 0.18 score to a 0.67. This isn't just a little better, it's a revolutionary leap in our ability to see these rivers accurately. So what this all means is that for the first time, we have models that can genuinely predict the complex, messy, real-world geometry of America's rivers. But hold on, because the story has one more really clever twist. You might think that they found one single magic algorithm that just worked perfectly everywhere, but that's not what happened. The real breakthrough was realizing that different kinds of rivers actually need different kinds of experts. What the researchers found was fascinating. For example, in the rugged, forested Appalachian Mountains, the random forest model was the champion. But then you go across the country to Mediterranean California, and suddenly the neural network was the star performer. It's because these AIs have different strengths. The random forest is great at finding clear rules in that mountain terrain, while the neural network can uncover the more subtle, complex patterns you find in California's unique climate. One size definitely does not fit all. And that led them to this brilliant multimodal approach. Think of it like building a dream team of specialists. Instead of using one general-purpose tool for every single river, you deploy the AI model that's already proven it's the absolute best for that specific region or that type of river. This way, you maximize your accuracy across the entire, incredibly diverse American landscape. So, what's the grand finale? What do you get when you put all this work together? Well, it's not just a better model. It's a real, tangible thing that anyone can use. A completely new, high-resolution atlas for all of America's rivers. And the scale of what they accomplished is just massive. Using that dream team approach, the team generated detailed geometry predictions for nearly 2.7 million individual stretches of river across the contiguous U.S. And this incredible public resource now has a name, StreamGeo. It's the culmination of this whole effort, turning a really complex AI research project into a practical tool that can be used for science and for managing our resources. So what's actually in this new atlas? Well, it gives us those high detail estimates for river width and depth. That's the stuff that's absolutely vital for better flood models. It also includes the width to depth ratio, which is a key number for scientists studying how rivers form and change. And it even calculates the total surface area of rivers and streams, which is super important for ecologists and climate scientists. And this isn't just something that's going to sit on a shelf. As the authors themselves put it, this is a groundbreaking new resource. It was built to be used to improve our flood warnings, to spark new ecological discoveries, and to give river managers better tools to protect all of us and our natural resources. You know, by finally moving past that 70-year-old formula and truly embracing the power of AI and big data, we've completely changed how we see our nation's waterways. We've created this incredible new map, not of roads or cities, but of the very arteries of the continent. And that leaves us with one really exciting question. Now that we can see our rivers more clearly than ever before, what will we discover next?